Hello, everyone. Welcome to your first video on newer material. What we're going to be looking at is marginal functions and economics. So this is kind of your first business application of the derivative rules and derivatives and how they fit essentially into a more real world setting. And so what we're going to talk about is really just kind of focusing on this word marginal and specifically what it means when we say marginal analysis. And so I've got this definition kind of written up here so you can kind of look through it and read through it. And if you want to kind of copy it down, you can. But essentially, when we say marginal analysis, what we're looking at is the study of the rate of change. And again, this should be really a sticking point now in terms of calculus, specifically of economic quantities. And when we look at economics and when we really look at this marginal, um, the idea of an economic analyst or even a business analyst, really any kind of social science, we're not just concerned with the value that something is right now, but we're actually equally concerned with how it's changing. In other words, are we growing or are we declining at this exact moment? And that's where this language of rate of change is really important, and we'll make that connection with what that means in terms of marginal. And we'll kind of do it in terms of starting out by looking at cost functions. And throughout this lesson, we'll kind of keep adding to this and dealing with what does marginal mean, how do I find marginal items. And so for us specifically, we'll start with cost functions. And so I have this problem as the applied example one, rate of change of cost functions. Suppose the total cost in dollars incurred each week by Polar Air for manufacturing X refrigerators is given by the total cost function C of X is equal to 8,000 plus 200X minus 0.2X squared. And X is going to range from 0 to 400. So essentially, we are producing from none to if we were to make up to 400 refrigerators. I can never remember how to spell refrigerator. It's always really, really fun. And so the first part is asking you to find what is the actual cost incurred if you were to produce 251. B, find the rate of change of the total cost function with respect to X when X is 250. And then we're going to compare the two answers here and kind of see what's the connection between this rate of change and what we're actually seeing in a total cost. So if you want to attempt this problem, pause the video now, go through and see if you can answer A, B, and C. I will go through and solve this out. I'll start with A, I will pause and then go B, pause, and then go into C to give you enough time if you want to double check work and answers. So try it now. Okay, so let's look at the solution for this. So let's go ahead and look at the solution. Let's say I'm going to pause. Okay. Let's go ahead and look at the solution then for part A and what it's asking me to do here. So it says, what is the actual cost incurred for manufacturing the 251st? So essentially, the assumption here is that we are making at least a fixed number, 250 refrigerators. And I want to know how much will it cost if I want to bump up production to 251. So I need to find the cost of producing 251 and subtract that by the cost of 250. And so you can use your calculator. You can do this by hand. Essentially, we're saying for this part, 8,000 plus 200 times 251 minus 0.2, 251 squared minus 8,000 plus 200 times 250 minus 0.2, 250 squared. So I'm going to go through and use my calculator and on my phone and figure out how much this would be. So I've got 8,000 plus 200 times 251 minus 0.2 251 squared. So I get 45599.8 minus 8,000 plus 200 times 250 minus 0.2 250 squared. 45500. So this tells me, subtracting these two values, I get 99.8 or $99.80. So if we were this company, if we were Polar Air, just to kind of analyze what we've got, we are currently making 250 refrigerators. And if I was to bump up the production to 251, it's going to cost me an extra $99.80. This is the exact cost for that. So for B is now asking, find the rate of change of the total cost function with respect to X when X is 250. Now, I mentioned earlier that rate of change, again, should really stick out in terms of what this is asking me to find. Remember that rate of change is the equivalent to derivative. So when this is telling me to find the rate of change, it's really asking me to say, or it's really asking me to find the derivative of my cost function. In other words, I want to find C prime of X. So I've got C of X was equal to 8,000 plus 200 x minus 0.2 x squared. I'm going to derive this. The derivative of 8,000 is 0. The derivative of 200x is just 200 minus the derivative here is 0.4x. And this problem gave me a very specific value. It says find the rate of change with respect to x when x is 250. So I'm going to go through and find C prime of 250. So that's going to be 200 minus 0.4 times 250. I'm going to use my calculator again for this because I don't feel like doing mental math. And I get 100 or $100. All right, and so let's talk about what this essentially means, because in C, and let me pause for a minute so you can look back at C and try to answer this. So I'll pause. Okay, so in C, we were asked to compare the results from A and B. So in A, we had the exact cost in producing the 251st, which was $99.80. In B, what we found was the rate of change of the cost producing 250 refrigerators, and we got $100. So notice how similar these numbers are. Now we are off by 20 cents, but if you're thinking about like analyzing and analysis reasons, 20 cents is actually not that big in terms of just deciding if I want to produce an object, how much cost would that give me? Saying something would cost me $99.80 versus $100 isn't a big difference and won't be a big deciding factor. It's a very, very good approximation. And so instead of having to go through and do like we did in part A to find how much would it cost to increase the next item, what we can do is use calculus like we did in part B, take the derivative and plug in our production to figure out what it would cost to make one more item. And this is essentially what marginal is referring to. Marginal is all about what does it take for the next. So if X is producing this, if we're at this production level, how much would it cost? How much would we make? What are the margins? What's the little bit left? and available for us. And so that's actually what I've got kind of defined here. So for our specific question, since we're dealing with cost, marginal cost is defined as the actual cost here incurred in producing an additional unit of a certain commodity, given that a producer is already at a certain level of operation. So again, we were assuming in that previous problem that we were producing 250 refrigerators. And so to figure out what would the actual cost be in producing an additional amount was by going through and finding the marginal cost function, which we defined as C prime, and then we plugged in or evaluated what we were producing at. And so this is how we can go through and figure out marginal cost and make decisions based on and make production decisions based on the data that we receive. Okay, so here's another example for you to go through and attempt to answer given with the new terms and definitions we have. So go ahead and pause the video and attempt this problem, and then I will go through and work on the solutions. Okay, so let's start going through and working on the problem. So what we have, a subsidiary of Electra Electronics, that's a tongue twister, manufactures a portable DVD player. Good thing we use DVD players now. Management determined that the daily total cost of producing these DVD players in dollars is given by that cost function there, where X stands for the number of DVD players produced. Find the marginal cost function. So we know that the marginal cost function, marginal, means find the rate of change. I need to find C prime. And so I'm going to go through and I'm going to derive each piece here. So the derivative of the first part is 0.0003 x squared minus 0.16x plus 40. And that's the answer to part A. There's my marginal cost function. All right, for B, what is the marginal cost when X is 200, 300, 400, and 600? So now we're going to use our answer from A, and I'm going to go through and find C prime of 200, C prime of 300, C prime of 400, and C prime of 600. And this is really just kind of plug in and chug. So I'm going to go and use my calculator, 0.0003, 200 squared minus 0.16 times 200 plus 40. And that will give me 20 or $20. For 300, again using my calculator, I get 19 or $19. For 400, I get 24 or $24. And then for 600, I get 52 or $52. All right, so there's our marginal cost for each thing, and C wants us now to actually analyze and interpret our results. All right, so I'm gonna give you a second. Go back and look at our numbers. What does each value mean? See if you can kind of put it in your own words, and then I'll kind of write out, at least for the first one, part A, what that's referring to. Okay, so interpreting our results. Remember that what C prime is representing is the marginal cost of producing one additional item given we are currently producing 200 items. So in this problem, 200 DVD players. So in other words, if I go through and I produce the 201st, if I want to go to the next item, what that $20 represents is it's going to cost me an extra $20. That's the cost to try and increase the production. Now, whether that's a smart move, we don't know. We have a lot of things to kind of balance that with, and we'll kind of keep digging into that and some other terms with that. But essentially, that's what each value represents. Notice that if we look at the very last number here in terms of cost, that's a huge cost in terms of producing one more item. So even if our current production is 600, just notice just by going to 601 how much more that is. And so this could kind of help you determine what your base production level should be. It almost seems like 300 is getting closer to kind of the optimal since the cost goes down from 200 to 300, but then jumps back up after 300. And so I would almost want to produce at 300, honestly, and try to find the sweet spot. But that would just be me. Okay, so the next topic we're going to look at is average cost functions. So let's let C of X denote the total cost incurred in producing X units of a certain commodity. This is the same thing that we are using for cost functions earlier. So then if I want to talk about the average cost of producing X units of the commodity, this is obtained by dividing the total production cost by the number of units produced. So when I want to do average cost, we're going to notate this. Oops, sorry about that. We're going to notate average cost being C bar. The bar means the mean. You see this if you've taken a stats course or if you are in an economics course, you'll see this kind of written. And so if I want to find the average cost, this means I'm going to take my cost function, C of X, and then I'm dividing it by the amount that I'm producing, which is whatever X is. So notice we're essentially saying, let's take the total production cost, divide it by the number of units. Well, this is C of X, this is X, and thus we have our definition here that we just set up. And so this is our average cost function. It just tells us again the average cost in production if we were to increase. It allows us to show us trends. And so here's a basic example. This will be applied example 3, the marginal average cost function. So what if we get into and look at the change of the average cost? So what we have is the total cost of producing X units of a certain commodity is given by the formula C of X is equal to 400 plus 20X, and this is in dollars. Find the average cost function C bar. We had that definition earlier. Then find the marginal average cost function C bar prime. And then what are the economic implications of the results that we got? Again, analyzing what we have. So quick pause if you want to and try this problem. I'm going to pause for a second and then get in to start working this. All right, so for A, I want to find the average cost function. Now, based on the definition we had a second ago, C bar is my cost function divided by X, the amount that we're producing. So for this problem, my function is pretty straightforward. It's 400 plus 20X, and then I'm going to divide this by X. And then I'm actually going to go ahead and simplify this by taking each piece in the numerator and dividing it by that X. And just kind of reducing and simplifying it. So I get 400 over X, there's nothing I can do there. But in the second term, I can actually get rid of these X's right here. And so I'm going to cancel those out. And so this is my average cost function. Now that's great and all. So let's move on into B, and then we'll kind of compare and take a look at what we got. So I'm going to now look at the marginal average cost function for C prime. If I want to find marginal, remember marginal means rate of change. It means find the derivative. So I actually want to derive the C prime function that we got in part A, that solution that we got. So I want to look at C bar, and I'm going to rewrite this so it's a little bit easier to derive. I'm going to rewrite it as 400x to the negative 1 and then plus 20. And again, my goal here is to derive this. Well, the first part is a product rule, or excuse me, not product rule, power rule. Negative 1 comes down, subtract 1. Derivative 20 is a constant, so the derivative is 0. And so this is actually my marginal average cost function, negative 400x to the negative 2. And to make it a little bit more useful, I'm going to rewrite it as negative 400 over x squared. And so that is our marginal average cost function. So for C, I want to go through, and again, I want to look at the implications. So I'm going to pause for a second, give you a chance to take a look at this. Go ahead and pause the video. See if you can figure out what do these two things mean and why are these useful for us. Okay, so one of the first major implications is to go back and look at the average cost function, so what we got in part A. And I want you to notice that for my average cost, there is a floor to how much this will cost us for our production. Because as x goes to infinity, if we were to increase production, this 400 over x is going to go to 0. Again, if you let x become very, very large, this first part is nothing. It becomes so insignificant. And all that's left is this plus 20. And so what that means is that my floor then is the average cost will go to $20. We had an example like this when it came to making money from movies. If you let time go on, at some point you're going to reach some kind of upper boundary in terms of how much money you'll bring in because people would have seen everything. And so in this situation for us, what's happening is as I produce more and more and more and more items, the average cost just becomes a fixed cost. It's just going to turn into this $20 and reach this floor. And we actually see this in terms of the marginal average cost. If we look at our answer in B, it's that notice how this overall derivative is negative, meaning that as I continue to produce more and more items, the cost is going to continue to drop because that's the change. And not only that, it's because it's over x squared, again, as x goes to infinity, the marginal cost will go to 0. And so as we produce more and more objects, there's going to be less and less and less change, which is what we see again in our answer for A, because we're going to hit a fixed cost. That marginal of continuing to produce is insignificant. And so it kind of makes a really good connection between the two for this problem. And so that's our first example. The next example that we're going to take a look at is this applied example 4. Marginal average cost function. And what we're going to do is we're going to kind of go back to that Electronics, who's making the DVD players, and look at it now in terms of this average cost and how this average cost is changing. And then again, kind of interpret it and actually sketch the graph, which I'll use Desmos for. So again, I'm going to pause for a sec, pause the video if you need to, go through and see if you can figure out this problem. And then I'll start putting up my work in case you need some help. You can play it and follow along. Okay, for A, so find the average cost function, C bar. Again, C bar, that average cost is my cost function divided by X, how much I'm producing. So in this example, C bar will be 0.0001 x to the third minus 0.08 x squared plus 40x plus 5,000 divided by X. So like in the last example, for my average cost function, C bar, I'm going to go through and divide X into every single thing. So I'm going to divide X into this part, use a different color. So X into here, 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 and here. And it's essentially just going to knock off one of the powers for each part. So the coefficients will actually stay the same. This will now be x squared minus 0.8x plus 40 plus, and here this will be 5,000 divided by x. And there's my answer for part A. For part B, find the marginal average cost function and then compute C bar prime of 500. So in other words, what's the marginal average cost if we were to produce 500 DVD players? All right, so marginal means I need to find the derivative. So I'm going to go through and derive. So I'm going to get 0.0002x minus 0.08. The derivative of plus 40 is nothing. 5,000 over x, again, when I want to derive something like this, it will be better to rewrite it as a power rule. And so this will be negative 5,000 x to the negative 2. And so this is my derivative. I want to go through and compute this at specifically 500 DVD players. So I'm going to get my calculator back out. And I'm going to get a really small number. And so we can go through and say that this is 0. So that the average cost at 500, its marginal average cost is $0 in terms of production. Okay, so C. C says sketch the graph of the function C bar and interpret the results obtained in parts A and parts B. So I'm going to go through and I've actually got this already done in Desmos. So I have my C of X done up here in the top left. I'm just going to kind of get that bar out of the way. And the window is not going to make a lot of sense right now. You shouldn't see anything. And the reason is remember, this is going from 0 to 400. So I actually really have to minimize this out until I can actually see the graph here. And I'm going to kind of fix the window so we can see it a little bit more like that. And so specifically, we want to focus on 500. And I'm just going to kind of click on that point right there so you can kind of see it. At 500, notice that the average cost, if we go from left to right, the average cost is decreasing like it was in the previous example until we get to 500. But after 500, notice that the average cost actually starts to increase. So as we produce more than 500 items, it's actually going to start costing us more as we go through. And this is kind of an interesting phenomenon because, again, in the previous example, our average cost would go to 0 and become a fixed rate in terms of how much we would spend. But here there seems to be an optimal option to choose from in terms of production. And I would almost take that in terms of you will reach a point in terms of making an item where it's going to start costing you more and more because of either overhead or working or fees, some other kind of cost that affects us here. That's not necessarily a fixed cost. And so that's what's kind of interesting. Now, the other thing is because this is decreasing until we get to 535 in terms of this graph, and I'll even kind of fix it in so you can see it there. We went through and for the derivative of this average cost, we got 0, which makes sense because that's the lowest point. The tangent line there would be perfectly horizontal. Its slope is 0. All right, so the next section, we're going to look at what's called revenue functions. Recall that what a revenue is the money that is brought in per item sold. So we can represent this as a function if we let X represent the amount of sales we have on whatever unit we have. So if the company, whatever company we're looking at, charges P dollars, then our revenue would be the cost per unit times X, the number of units. And you can see this formula given by this right here. So R of X would be equal to P times X. And what gets interesting about this, and which you'll see in the next paragraph, is that the price that we choose per unit is a function in and of itself, because that price is dictated on many, many different markets, and depending on which situation we're in. For example, if this was a monopoly, then we would be able to dictate the price to be whatever we want. If we are in a fair market and in true competition, then X is determined, or excuse me, the cost is determined based on a competitive with other corporations and trying to make sure we're the lowest price, but still making the most we can out of it. And so we base essentially P and X off of what's called this demand equation, which we have looked at beforehand. In solving this for P, we get that function where P is going to be equal to some function F. It's just going to involve X's. You'll see this in the next kind of example. And now we have what's known as a unit price function F. So P is equal to something in terms of X. Well, this means that because P is equal to this function right here, if I look at my revenue formula, which is P times X, well, P is F of X, so therefore my revenue function can be given by X times F of X, X times whatever that model is for my unit price function. So I've got an example here that we'll get into in a second because this is my revenue function, but what we're going to look at is the marginal revenue. And then within that, the marginal revenue function. So the marginal revenue is the actual revenue realized from the sale of an additional unit of the commodity, given that sales are already at a certain level. So given that we are where we're at and we know we've sold this much, if we were to sell one more item, how much revenue would we make? Would it be an increase or a decrease? And if I take X to be variating for this marginal revenue, we can get a function for this just like we did before. This function is the derivative since we're dealing with the marginal. And if I derive R of X, this will measure the rate of change of that revenue function. And so here's an example. This is applied example number 5 that deals with the marginal revenue function. So suppose the relationship between the unit price P in dollars and the quantity demanded X of the Acrosonic Model F loudspeaker system is given by the equation P is equal to negative 0.02 X plus 400 from 0 to 20,000. Find the revenue function R, so just what is the function? Find the marginal revenue function, so what is R prime? And then compute this marginal revenue at 2,000 units sold, demanded. And then we'll interpret the results and take a look at that. So I'm going to take a pause. Feel free to pause the video, and then I'll work through it. Okay, so first thing I need to do is find the revenue function. Now remember the revenue function, as we just defined, is defined as X times P, or P times X. P here is given by this function. So this will be X times negative 0.02 X plus 400. And to simplify this, I'll distribute negative 0.02 X squared plus 400X, and done. There's my revenue function. So this will compute for any quantity demanded. We can find out how much money we would bring in from that. B, find the marginal revenue function R prime. So this means I need to go through and derive my revenue function. I'm going to apply power rule, so this will be negative 0.04x plus 400, and that's it. Pretty straightforward. For C, it says to compute R prime of 2000. So I'm going to take my answer in B, and I'm going to plug in 2000. Use my calculator to evaluate this. So negative 0.04, 2000 plus 400 to 320, or $320. And so what this means is that, we're already producing 2000, but if I was to produce the 2001st speaker, we would bring in a revenue of $320. And so that's marginal revenue, and specifically working with the marginal revenue function. Okay, so the last function that we'll look at and really try to interpret and work with in terms of derivatives and this idea of a marginal is profit functions. So profit functions take revenue and cost, two of the functions that we've been looking at prior, and is the subtraction between revenue and cost. Because if we look back at revenue, one of the important aspects just to remember is that revenue is just the money that you're bringing in per quantity sold. It's not necessarily how much money that we're actually making off of what we're selling, because we haven't actually taken into account yet how much it costs to produce that item. And so that's why you'll see the profit formula as the subtraction between these two functions, this algebraic operation here in combination. And so then if I want to start looking at this profit as a function, then we can also start looking at it in terms of, if I'm producing X amount of items, what kind of profit would I get if I was to produce the next one? So you see at the end of this marginal profit definition, the X plus 1st unit, and specifically kind of focusing on the actual profit or loss realized from going this one extra step. And so that's what the marginal profit function tells me, is it's allowing me to look at how the profit is changing as I increase to the next item being created and sold. And so I've got an example. This example is applied example 6. It is the marginal profit function. Refer to example 5. Suppose the cost of producing X units of the Acrosonic Model F loudspeaker is C of X is equal to 100X plus 200,000 in dollars. Find the profit function P. Find the marginal profit function P prime. Compute P prime of 2000 and interpret your results. Sketch the graph of the profit function P. R of X is equal to negative 0.02X squared plus 400X. This is from referring to example 5 and reusing our answer from that. And so I'm going to go ahead and pause. I've actually already worked this one out, so I'm going to give you a second to work this, and then as you continue, I'll scroll down so you can kind of see my work. We'll talk about D and talk about C in terms of interpreting the results. All right, so I'm going to scroll down so you can kind of see my work for this. So for an A, if I'm going to do the profit function, I need to do my revenue minus my cost. So my revenue from example 5 minus the cost function that's given. And then I've just simplified the red arrows. Just remember that this minus is distributing, so it's a really easy mistake to make. I've got negative 0.02x squared plus 400 minus 100x is 300x minus 200,000. And so this is my profit function here. Now, to find the marginalized profit for B, we're going to go through and derive this. And so I get negative 0.04x plus 300. And then if I want to compute P prime of 2000, which you see in C, P prime of 2000 is equal to negative 0.04 times 2000 plus 300. This comes out to be 220 or $220. And then in the sketch, you'll see I've got just a basic sketch here. of what this function looks like. Essentially, the idea is notice how the profit function itself continues to increase until it reaches the peak and then it decreases. Well, where the marginalized profit function and these numbers help us is at that peak, P prime of X is 0. The marginal profit is nothing. And that should make sense because as our profit is increasing, we're earning more. So we're getting, my marginal is positive. It's going to be 0 at this highest point, and then my marginal profit will begin to be negative because we're actually going to be losing money if I continue producing more or the next item and the next item and the next item. And so it helps me to optimize exactly where we should produce and how much we'll sell, so that way we have the highest profit. And so that's why what we're looking at now is very foundational to what we'll continue to see throughout. And also one of the hardest things in calculus, which is optimization, which we'll look at not in the next section, but the next section, getting a little bit closer to the end of this module. So attached, you'll have some practice problems taken from the book. I will post answers to the selected ones. And then if you have any questions or you want to see how things are worked, definitely post in the group me, send me an email, or see me during my office hours, mostly from 4 to 4:30, except on Fridays. And that's it. Thank y'all.